Okay, so we've got a few things here. We have our equilibrium length for the joke glasses, and then it goes out, and this is 0.1 meters. It goes out to 0.26 meters, and then it shrinks to 0.012 meters. And what we want to know is how much is the energy in the springs reduced, presumably from the maximum length down to the shortest length. And so what we're looking for is the change in the potential energy. So in order to find that, everything's got to be measured. Well, if you recall, potential energy for a spring is equal to 1/2 kx squared, where k is the spring constant, x is the distortion from equilibrium. So for the first bit, the extortion from equilibrium is this piece here. That's going to be 0.16 meters. And for the second bit, the distortion is this distance here, which is going to be 0.088 meters. And so what we need to do is we need to find the potential energy here, we need to find the potential energy here, and then just subtract the two. Is that enough, Brad, or do you want me to keep going? You sure? Okay. Any other comments, questions, concerns, or does anyone want me to do the rest of this? When we finish the question? Okay. So if we're going to find we've identified kind of the three states: equilibrium state, long state, short state. We just need to find this potential energy and this potential energy. So one of them is going to be PE initial is going to be 1/2 times 25 times 0.16 squared. PE final is going to equal 1/2 times 25 times 0.088 squared. This value is 0.32. This value, if you punch in your calculator, should be 0.0968. And so if you subtract these things, you're going to find that the change in the potential energy, or it's reduced by 0.2232. And that should be negative joules. Yeah, Brad?
Is it not like for the 0.088 is negative because it's like on the other side of the
Yeah, but you're squaring it, and it's going to make it positive anyway. Yeah. You're right. It's a reduction in length. It should be negative, but you're squaring it, so it doesn't matter. Okay, all the rest of that makes sense? Yeah. Anybody else? Anything from work energy or spring potential energy? Going once. Yes, Alana. On the springs? Previous page. Question 8, the puck. Okay. So you've got a 2 kilogram puck accelerated at 5 meters per second for 0.5 meters across a frictionless air hockey table. How much work was done by the puck? So you're looking for work. I did manage to cram it into this line, which is really not what you should be doing, but for someone else's benefit, I did that. Work is equal to a force times a distance. Work could also be equal to change in energy. So you can do this one of two ways. You can look at, because you have acceleration and you have a distance, you can look at initial velocity and final velocity. Assume initial velocity is 0. You can look at the final velocity and see what the change in kinetic energy is. Or you can look at it as work equals a force times a distance. You have the distance, and the applied force is the only force acting in the direction of motion. So then I used F net equals ma. The applied force is the net force because that's the only thing that's acting. There's no friction. We know the mass, we know the acceleration, so I can find the applied force. Multiply 2 and 5 together, get an applied force of 10. and then that's going to be F, and the distance is 0.5 meters. So then you're going to get a work done of 5, I think. 5 times 2 is 10 times a half is 5. Yeah. Does that make sense? You can do it either way. Yes, Riri. Number 5 on the spring one, sure. A man with a weight of 900 newtons lies down on a spring-loaded mattress. The combined constant of all the springs in the mattress is 18,000 newtons per meter. How much elastic potential energy is stored in the bed's springs? So, how did I do this one? Yes. Cool. So, PE equals 1/2 kx squared, and we're looking for PE, we've got K. K is 18,000, so this is going to become 1/2 times 18,000 times something squared, and we need to figure out what this x here is. We are told that he has a weight of 900 newtons. So to find the extension, we're going to have to bring this back to something we did last chapter, where we looked and saw that the force of, well, I'll write it out this way. F net equals MA. A is equal to 0 because the guy's just sitting on some springs. The net force is the spring force minus the gravity is equal to 0. So the spring force is going to equal Fg. The spring force is equal to Kx, and Fg is equal to 900 because we're given that. We know K is 18,000. So 18,000x is going to equal 900. So the extension is going to have to be 0.05, 900 divided by 18,000. And that's going to be in meters. You take that value, you plug it in there right there. Now that we know how much the springs have been compressed by, we can figure out that the amount of energy stored in the bed of the spring is just going to be these three things multiplied together, and you should get 22.5. Does that make sense? I was bringing back this from last chapter to find the extension. Jack, good morning, sir. What was the last movie you saw in theaters? Okay. It's been that long, eh? Okay, anybody else? Comments, questions, concerns on anything we saw last couple days? Brad, last one. Okay.
I'll just ask you later.
You sure? Okay. Yes, second to the first one, last potential. This will be the last one. Okay. So, fun one. Keys on a keyboard contain small springs that compress by 4.8 millimeters. So what we're going to do is we're just going to take that right away and turn that into meters. There are 1,000, milli means 1,000, so there's 1,000 millimeters in a meter. So we're going to divide 4.8 by 1,000, and we're going to get 0.0048. And we make 12,500 keystrokes. Every time you hit the key once, you're imparting potential energy, and then the keys are going to depress. Sorry, the springs are going to, the key's going to come back up and decompress. Keys are coming back up, releasing the energy you just gave it. So what you want to find out is the sum of all of the energy that you've given it. So if you do this many times, that is equivalent to doing it once, one really big compression. So if we're looking for the energy supplied to the springs, PE is going to be the energy the amount of potential energy that all the springs gained over the day is the amount of energy that we gave. So we're just looking for PE. PE is equal to half kx squared. So we're going to have 1/2 times 2.5 newtons per meter. That's the constant. And then this is going to be 12,500 times 0.0048 squared. And that's all of it. You can think of a whole bunch of little compressions as one big massive compression. Does that make sense, Cal? And I don't remember, 150, I think is the number that you're looking for there. Okay, let's take a look at today. Hopefully the stairs didn't burn you out because y'all are going to go run them. Today we're looking at power. Oh yeah, here we go. Okay, flip back, find me this page. This is previous to what you've looked at already. I know at least one of you has tried to do this several times on your own, and that's fine, I guess, sort of, but, you know, don't destroy all my thunder. So we've got work and we've got energy. We've defined work a couple different ways. We defined a bunch of different kinds of energy. We looked at spring potential, we looked at gravitational potential, we looked at kinetic. Those are kind of the big three. Everything else is going to get lumped into this idea of work. Because, yeah, I've given you 3 specific examples of energy, but then I also told you guys that work is defined to be a change in energy. So even if we don't have kind of a definition for a particular kind of energy, we can still look at how much work went into making that energy happen. We've also got the fact that work is equal to a force times a distance. And so what we're going to do is we're going to take all those concepts and we're going to look at, yes, they've been done, but how fast have they been done? And the speed at which work is done, or the speed at which energy is changed, we define to be power. That is the definition, the physics definition for power. How powerful are you? How fast can you do the work required of you to do? So we've got some definitions for that. Whenever we want to know how quickly something's done, we take a concept and we divide it by what? If you want to know how quickly something's done, you divide what was done by time. So power is if it's how quick you can do work, it's going to be work divided by time. But if you take a look at what we've got here, so we've got a couple expressions here for this now. We said one, that work is equal to a change in energy over time. So we're going to use this definition at least a little bit. Let's zoom in here, make this easier to see. But alternatively, we said that work was equal to a force times a distance. So I can replace work with force times a distance divided by a time. And if you look at what happens here, this is kind of an interesting result. If work is equal to a force times a distance, what's d over t? It's the velocity. So this is going to equal force times how fast the object's moving, which is kind of a weird way to think about power. But, I mean, mathematically it works. I'll show you examples of where we use one versus the other. If you recall, this d divided by t is equal to v. What kind of v is this? It's this particular kind of v. It's not, well, I mean, it's speed if you ignore the direction. What is v if v is equal to d over t? Say that louder, Raina. You might be right. You sure? Okay. If v is equal to d over t, that means v isn't changing. It means this v is constant. So if you're given a constant velocity, you can multiply. That's what you said, isn't it? I'm pretty sure I heard you. Have a little bit more faith in yourself. V is equal to a constant velocity. I wouldn't call you out if what I thought I heard was wrong. Okay, so let's look at what these things are measured in. We've got a few different expressions for this. Power is equal to work over time. Work is measured in. What are the units for work? Sorry? Joules, because work is a change in energy. So power is either going to be measured in joules per second. Sorry, yes, joules per second. Or if you look over here, F is measured in newtons. D is measured in meters. T is measured in time. So power is either going to be measured in a joule per second or a Newton meter per second. But that's kind of a really lame way to define power. It's more convoluted, and we've got a special someone who did a lot as it relates to power, and so we're going to take his name and we're going to slap it on power, and we're going to forget about joules and seconds. Who's the guy that did a lot of work with power? Or what is the other unit you are familiar with as it relates to power? I look at a power rating on a light bulb, for example, or a power rating on a motor. Yeah, it's in watts, kilowatts. So power is measured in watts. James Watt is the name of the guy. British? Or was he American? Either way, he wasn't Canadian, so we don't care about him. That's not entirely true. So a watt is equal to a joule per second or a Newton meter per second. And power is commonly referred to in horsepower. When you are looking at vehicles, trains, cars, mostly trucks, things that have a lot of it, we often refer to it as horsepower because power was at one point related to the most powerful animal people used, put to work, and that is the horse. And so how much power a horse has was deemed to be 746 watts. So whenever we look at these things, we can figure out how much horsepower is available by taking however much power there is and dividing it by 746. We're going to figure out how much horsepower was involved in a particular act. So I'll do a couple examples, and then you guys are actually going to go ahead and do a lab. You're going to calculate your power. Here's the first example. If a 30-kilogram object is lifted 20 meters straight up in 2 minutes, what power was used to make that happen? So I'm going to draw a line down the middle here, and we're going to do this question 2 different ways. On the left-hand side here, I'm going to draw this scenario. You've got an object. We don't know where the object starts. It doesn't tell us where the object starts. It just tells us that the object is lifted 20 meters straight up. So it could start at 10 meters and go to 30 meters. It could start at 5 meters and go to 25 meters. Or I could just as easily start at the ground, because why not, and be raised 20 meters. So if we use the work as defined as a change in energy, what kind of energy are we changing as we raise the block? Gravitational potential energy, yes. So power, P, is going to equal to the work divided by the time, which is going to equal the change in energy divided by the time, which is going to equal energy final minus energy initial divided by the time. And so then this is going to go ahead and be potential energy gravitational final minus potential energy gravitational initial, and how much potential energy does it have to start? 0. 0 makes sense. It makes sense to call this height down here height 0. So then this is gone. There is no initial gravitational potential energy. So then power, divided by time. So then power is just going to equal mgh final divided by how long it took to do that. So that's just going to be mass, which was 30, times 9.8 times 20. I just ran out of space. That's okay. Divided by the time, and the time should always be in seconds. So 2 minutes is how many seconds? 120. There's 60 seconds in a minute. So 2 times 60 equals 120 seconds. So that's just going to go in here. And we're going to find out that the power required to do this is 49 watts. So if you were trying to do this with a motor that had a lower rating than that, you're probably going to burn out the motor. For example, if you're trying to do 49 watts worth of work with a 40 watt motor. Does that help, Harley? If I zoom in a little more? Yeah. Yep, you do it. Okay, that's one way to take a look at this. Another way to do the exact same question is to use a different definition for work. We can say, okay, I'll start it again. Power is equal to work divided by time. But this time, instead, we're going to say that work is equal to a force times a distance divided by the time. Now, if I go over here to our picture and I draw a free body diagram, what are the forces acting on the block? There's going to be an Fg downwards, but we're lifting the thing. So as soon as it leaves the ground, Fn is gone. But to lift the thing up, there has to be an applied force up. So we're going to replace Fn with Fa. Because as soon as the work begins, Fn's done. It's gone. So if this thing is, and if you don't know, you have to assume if it's being lifted, the simplest way for this thing to be lifted, or the least case scenario where this thing is actually lifted up off the ground, is when these two forces are equal. That will give you a lift at a constant velocity. If acceleration equals 0, that means F net equals 0. It means F A minus Fg equals 0. It means Fa equals Fg. An argument that I made a whole bunch last unit. And I'm still operating under the assumption that those tests went well. So we're just going to say that we learned it last year because I haven't looked at them yet. We're going to say that that went well. And so then the applied force upwards is equal to the force of gravity downwards. And so what that's going to give us is it's going to give us that this applied force upwards doing the work is equal to Fg downwards times the distance traveled divided by t. But look at this. If Fg is the force downwards, Fg is just equal to mg. The distance the thing traveled was the amount of height it was raised. So d can just become h. And then time is time. These two expressions turn out to be identical. Whether you look at a force applied times the distance traveled divided by time, or if you look at it a change in energy, you're going to get the exact same results. So then this is just going to become 30 times 9.8 times 20 divided by 120, and you're still going to get that the power is equal to 49 watts. It doesn't matter which expression you look at to solve the problem. You're going to get the same results. Which is kind of fun. Okay, now for something totally different as it relates to power. Let's take a look at a kettle. If you have an electric kettle at home, they're going to be rated for a particular power. You can find that usually on the bottom or on the back. Where is it on this one? Where is the power rating of my kettle? There it is. It's imprinted on the plastic on the bottom. This kettle right here is a 1500 watt kettle, or a 1.5 kilowatt kettle is what this is. This particular question says, how much does it take a 2 kilowatt kettle? Remember, kilo means 1,000, so this is going to be a 2,000 watt kettle to do 15,000 joules worth of work. Now, how much work is 15,000 joules? We'll look at that this unit. How has the temperature of the water changed if 15,000 joules of energy has been put into the water? We'll look at that, but not right now. So if I have 2,000 watts doing 5,000 joules worth of work, let's go ahead and figure out how long that's going to take. Power is equal to a change in energy divided by the time. That's the definition we're going to use here. The change in energy was 5,000 joules. Or how much work was done was 5,000 joules. Sorry, 50,000 joules. So this expression is going to become, we know how much power is provided by the kettle. The kettle is a 2,000 watt kettle, and that's going to be equal to 50,000 joules worth of work done, or energy imparted, divided by the time it took to do that. And so now we just want to isolate this thing for T. In order to isolate this thing for T, what do we have to do? How do I get T alone? Brad.
Take the 50,000 to the other side.
That will leave T alone, but it'll leave T alone in the denominator.
Oh, okay.
We don't want that. Multiply both sides by T. It's going to cancel on the right-hand side. Divide both sides by 2,000. It's going to cancel here. And you're going to be left with time is equal to 50,000 divided by 2,000. Those 3 zeros are going to cancel out with those 3 zeros. And 50 divided by 2 is going to be 25. 25 what? What are the units on time as it relates to power? Seconds, I heard someone whisper. So 50,000 joules must not be a lot if a 2,000 watt kettle can impart that much in 25 seconds, and that's not going to bring water to a boil. Yeah, you bet. We'll look at how much that changes the temperature of the water later this week. That last one, and this is what you're going to do now. After I do this example, we're going to get ready, and you guys are going to go out and you're going to run some stairs. An 80 kilogram person, you need to figure out what your mass is. I have 2 scales that we can use to do this. An 80 kilogram person can run up a flight of stairs in 2.1 seconds. You are going to measure how long it takes you to run up a single flight of stairs. I don't want you to do the corners. You're just going to go one straight flight of stairs. You're going to run it and figure out how long it takes you to get from the bottom to the top. If they gain 1.7 meters, you're going to find out what your height gain is in the time it takes you to run up those stairs by measuring a single stair and then multiplying all the stairs together. Because presumably, if the building was constructed properly, every stair is going to have the same height. If it doesn't, people would be tripping up the stairs all the time. We want to figure out what then is the power of this person. And you're going to do the exact same thing. You're going to figure out what your power is, both in watts and in horsepower. So here's what's happening. We have a person on the ground, and we got a bunch of stairs. Do, 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 do. This is an inaccurate drawing because according to the picture, this is 1.7 meters. It might not be an inaccurate drawing. Maybe a short person, maybe my daughter, then that would be accurate. You guys aren't going to measure this height. What you guys are going to do is you're going to measure the height of one of these stairs, and then you're going to multiply by all of the stairs. But for this particular problem, I give you the height of all of the stairs. The height of all the stairs is 1.7 meters. So power is equal to work over time, and we're going to use the definition of change in energy over time. And so that's going to be equal to what kind of energy have you given the person as they've run up the stairs? They start not moving, they end not moving. So what have you done to them? Sorry? Because potential. Because you're not sitting that far away. So this is going to be a change in gravitational potential energy divided by how long it took. Now, presumably, to make our calculations nice, let's call this height 0, because why not? Which means this top height is just going to be 1.7 meters. That line should have been straight. So then, power is just going to be the potential energy gravitational final minus potential energy gravitational initial, and this is 0. So P is just going to equal mgh, divided by time, mgh final divided by the time it took to do that. So this person can be found to have a power of 80 times 9.8 times 1.7 divided by 2.1. I will give you that value. The power of this person is 634.67 watts. If I want to take that and I want to convert it into horsepower, we're going to divide that value by 1 horsepower, which was 746 watts. And that's going to equal 0.85 horsepower. Now it's your turn. Questions, comments, concerns about what I've done here before we go run some stairs? One horsepower is 746 watts. Okay, here's what I want you to do. If there are no questions about the example we just did, what I want you to do is I want you to flip ahead to what I have called the Stairmaster Lab. And Stairmaster is trademarked, not by me, but by the people who own Stairmaster. And you're going to do this as a lab and you're going to hand it in, which is why there's nothing on the back page. Here's what you're going to have to do. You are going to be in groups of 3 or 2 or 3, doesn't really matter. You're going to determine the mass of each student in your group. I have scales for this. You are going to measure the height of one stair, and you're going to count all the stairs, and then you're going to calculate the height that you've gained by running up those stairs. You're going to do a practice run or 2 to warm up. No one should do this exercise cold. You should never do exercises cold. You should warm yourself up a little bit. So walk the stairs a couple times, run them once, kind of at a gentle jog, get yourself primed, and then I want you to go full up. As much as you're willing, run as hard as you can to figure out your maximum horsepower up the stairs. You're going to do it twice, like officially twice, because students ask about this all the time. What if I skip stairs? I think I can do it better if I skip stairs. Okay, cool. So your first time I want you to do it, I want your feet to touch every step. The second time you do it, I want you to count. You can skip as many steps as your little legs are willing to stretch. If you can do it 2-step skips, go for it. Do it however you want. Figure out what your power is in both cases. And then in both cases, what I want you to do is, you'll have done it twice here. Calculate the work done and the power of each student. The work will be the same in each case. You're still maximizing. You're still going up the same height. The only difference between your 2 runs could theoretically be the time taken You might have, the time will change depending on if you skip steps or if I force you to touch each step. So here I should have actually dropped a vertical line here, because I want you to find both powers. Power for the time 1 and power for time 2. I want to see one example of your calculations. How did you calculate this? Just do it once. I don't need to see all the calculations. Once you've done it once, you can either do, or you can do them on the back if you want, or you can just ram. Once I see it once, you can just ram it through your calculator. And then there's some questions down here at the bottom I want you to answer. How much work done by each student? What single variable determined who did the most work? Does the amount of work done by the students depend on how fast they climb the stairs? Look at the power output of each student. Although the standard unit for power is the watt, the power, I would calculate your horsepower down here, for both times, for 1 and for 2. And then there's just a conclusion there at the bottom, relating work and power together. This is going to be your activity for the rest of the class. Questions, comments, concerns. Oh, and then there were 3 questions that I didn't assign yesterday that are all relating to power. This is now going to be your homework today as well. Those 3 questions plus this lab. So, if you have no questions for me, get yourself into groups of 2 or 3. Make sure any measurements you take are done in centimeters so that they are easily converted into meters. See if you can figure out and you're going to report out on this. We're going to put your powers on the board and we're going to figure out who the most powerful person in the class is. It's going to be great. Okay, here we go. I have some measuring devices. 1, 2, 3, 4, 5, 6, 7. I got lots. Okay. And the scales are right here. You need your mass in kilograms. One right here. Sure works. Oh yeah, we're good. Cool. There we go. Mass in kilograms. Wait, what? All my rulers are over here next to the printer. Everyone needs their mass. And guys, be real clear. I want it one straight flight of stairs. You'll lose time on the turn if you find a curved stair. Find any set of stairs that you like. Please keep it close-ish, but yeah, one straight set of stairs. Straight set of stairs. It has to be a stairwell flight of stairs. You are not to go past the rotunda.
Wait, so for this first one, like, these 2 R's.
Yeah.
Like, R's 3
No,
times.
your partner. No, your partner.
Oh, okay.
No, because you need your mass. Okay.